To build the pipeline from scratch, we focus on loading and inspecting the BreastMNIST dataset, pre-processing it with normalization and reshaping, training a simple CNN with augmentation, evaluating metrics like AUC and confusion matrices, and deploying a TensorFlow.js model with an interactive front end. The goal is to create a robust end-to-end process that integrates Grad-CAM visualizations and client-side inference. Do you want to prioritize optimizing the current CNN or directly compare its performance with ResNet18 during this rebuild? ResNet18 performs better than your current CNN because of its deeper architecture and residual connections, which help address key challenges in training deep networks. 1. Depth for feature extraction. ResNet18 has 18 layers, which allow it to extract more complex and hierarchical features compared to your simpler CNN. Deeper networks can capture subtle patterns, like textural differences in medical images, which are crucial for distinguishing between benign and malignant samples. 2. Residual connections prevent degradation. ResNet18 introduces shortcut connections that skip layers, addressing the vanishing gradient problem common in deeper networks. These connections allow the model to learn residual mappings, the difference between the input and output of a layer, ensuring that deeper layers still contribute meaningfully without degrading performance. 3. Wider representational power. With more filters and layers, ResNet18 can represent more diverse features, which is particularly useful for BreastMNIST data if the images have high variability or subtle distinctions. 4. Generalization and pretraining. ResNet18 is often pre-trained on large datasets like ImageNet, providing a strong starting point for transfer learning. Even if you train from scratch, its architecture is optimized for robustness and generalization. In contrast, your current CNN is simpler, which makes it faster to train, but potentially less capable of capturing the full complexity of the dataset. ResNet18 strikes a balance. It's deeper and more powerful, but still efficient enough for tasks like BreastMNIST classification. Your current CNN model is scalable, and it can be made more complex if absolutely necessary. The architecture you're using is a foundational CNN with standard layers, making it relatively straightforward to expand or enhance. Here's why and how it could be scaled. Why the current CNN is scalable. 1. Modularity. Each component, convolutional, pooling, dense layers, can be extended incrementally without redesigning the entire architecture. 2. Efficiency for simple datasets. For datasets like BreastMNIST, the current model is sufficient for quick iterations. If performance improves with parameter tuning or better pre-processing, you might not need to switch to a larger model. How it can be made more complex. 1. Increase depth. Add more convolutional layers to extract deeper features. This increases the model's capacity to recognize subtle patterns. 2. Widen layers. Increase the number of filters in each convolutional layer, which allows the model to capture more feature variations. 3. Incorporate residual connections. Borrow concepts from ResNet by adding shortcut connections to help deeper layers contribute effectively without causing degradation. 4. Add specialized layers. Include attention mechanisms, batch normalization, or dropout layers to improve generalization and stability. 5. Switch to transfer learning. Integrate a pre-trained backbone like ResNet18 or VGG and fine-tune only the classification head. Practical recommendation. For now, keep the model simple and focus on improving training with better pre-processing, balanced datasets, and parameter tuning. If the performance remains suboptimal after these optimizations, scaling the current architecture is a logical next step before jumping to a heavier model like ResNet18. This way, you maintain efficiency while exploring complexity only if absolutely necessary. Splitting the training code into modular sections will make it more manageable and allow you to focus on improving each stage independently. Based on what you've outlined and the requirements, the next steps for the development of the training pipeline involve breaking it into these key modules. 1. Data loading. A script dedicated to loading the .npz dataset, extracting the training, validation, and test splits, and verifying the integrity of the data, e.g., checking for missing or corrupted entries. This module can also include reshaping and scaling the images to ensure consistency before further processing. 2. Preprocessing. This includes normalization, resizing, and handling class imbalance. Use augmentations or oversampling to address minority classes. Ensure the outputs are structured and ready for the training stage. Save pre-processed data if needed so it can be reused without repeating this step. 3. Model definition. A standalone module to define the CNN architecture. This keeps the model structure separate and allows for easier experimentation with different architectures or parameter tweaks. You can include functions to load pre-trained weights or create the model from scratch. 4. Training logic. This module handles the training loop, callbacks, e.g. early stopping, checkpoints, and logging of metrics like accuracy and loss. Include visualization generation, such as training curves, confusion matrices, and Grad-CAM heat maps. The training script should call functions from the data loading and pre-processing modules. 5. Evaluation and testing. A separate script to evaluate the trained model on the test dataset, calculate metrics, and save results. This ensures the training and testing processes remain independent. 6. Deployment preparation. A script for exporting the trained model into formats like .keras, .h5, or TensorFlow.js for deployment. Include testing of the exported model to verify consistency between training and deployment environments. 7. Visualization. A dedicated module or function for generating visual outputs, including training validation loss and accuracy plots, Grad-CAM heat maps, and confusion matrices. These can be integrated into the front end for better presentation. Next steps. 1. Split the current monolithic script into these sections, ensuring each module has a clear input-output flow. 2. Start with the data loading and pre-processing modules, as these form the foundation for the entire pipeline. 3. Refactor the training logic to call these modules and ensure modularity. 4. Plan for testing and debugging each module independently before integrating them back into the pipeline. Here's a practical project structure that organizes your training pipeline into clearly defined files and folders. The project structure includes a data folder for raw and pre-processed datasets, a models folder for model definitions and saved models, a training folder for scripts handling data loading, pre-processing training and evaluation, a visualizations folder for accuracy plots, Grad-CAM heat maps, and misclassified images, a results folder for logs and performance metrics, and a front-end folder for web deployment files like index.html, main.js, and style.css. There is also a README-MD for project documentation and a requirements text for dependencies.
Just a quick question about the front-end folder. If the index.html, should the index.html just be in the main folder so we can actually deploy the whole folder?
Yes. Placing the index.html in the main folder is a good idea if you plan to deploy the entire folder directly. This simplifies deployment because many web servers and hosting platforms automatically look for index.html in the root directory as the entry point for the application. However, keeping the front-end files in a dedicated front-end folder helps maintain a clean structure, especially in projects with multiple components like data, models, and training scripts. In this case, you can adjust your deployment configuration to point to the frontend/index.html file. The choice depends on your priorities. Simpler deployment. Place index.html in the root directory. Better organization. Keep it in a front-end folder and adjust deployment settings accordingly.
With the models, where do you actually get the ResNet model from? Is it the Python code that we can generate from scratch, or are we downloading the model from somewhere? I actually have a preference to generating everything from scratch if possible. What eventually should be in the web model folder? What type of files? I assume that's the one we deploying using JavaScript onto the front end. Now with the Grad-CAM heat maps, are we just doing it for a single example image, or we can select which image we're doing it for, or are we doing it for all the images if not way too heavy? Do you, by the way, remember how many images are currently in this dataset?
ResNet model origin. You can either 1. Generate it from scratch using Python code, This means defining the ResNet18 architecture yourself in a Python script using libraries like TensorFlow or PyTorch. This approach aligns with your preference for generating everything from scratch. 2. Download pre-trained weights. Pre-trained ResNet models are often available from TensorFlow or PyTorch model hubs. You can use these as a starting point and fine-tune them on your dataset. If you prefer generating from scratch, you can programmatically define ResNet18 following the original paper's architecture without relying on downloaded weights. Let me know if you'd like a detailed breakdown of the architecture. Web model folder content. When deploying the model using TensorFlow.js, the web model folder should include the following. 1. Model.json. This file contains the model architecture and metadata in JSON format. 2. Binary weight files. These are .bin files that store the weights and biases of the model, split for efficient loading in the browser. TensorFlow.js creates them during the conversion process. 3. Optional metadata files. If needed, you can include metadata describing the model's training or usage for better integration into the front end. Grad-CAM heatmaps. Single image. The current implementation appears to generate Grad-CAM heatmaps for individual test images, particularly focusing on misclassified ones. This is computationally efficient and useful for debugging. Multiple images. You could allow selecting specific images, e.g. from a drop-down or grid in the front end. This avoids overloading the system while keeping interactivity. All images. Generating heatmaps for all images would indeed be too heavy, especially for a large dataset, and is not practical for deployment. Dataset size. The BreastMNIST dataset has 546 training images, 78 validation images, 156 test images. Each image is 224 by 224 pixels in grayscale, making the dataset manageable for most operations. If heatmaps are needed for all test images, 156, it might be feasible, but for larger subsets like training or validation, it could strain resources. Let me know how you'd like to handle these aspects, and I can help refine the approach. The next steps for code development based on our discussion are: 1. Split the code into modules, data loading and preprocessing. Create a script, dataloader.py, to handle loading the BreastMNIST dataset, normalizing, reshaping, and augmenting the data. Include a class balancing mechanism. Model definition. Move the current CNN model definition to a separate script, baseModel.py. Optionally, define ResNet18 or other architectures in a similar manner for comparison. Training script. Refine train.py to focus on training and evaluation, pulling preprocessing and model definitions from the above modules. 2. Visualizations and results. Generate and save Grad-CAM heatmaps for misclassified images. Ensure they are limited to manageable subsets, e.g. test misclassified images. Save performance metrics, e.g. accuracy, AUC, confusion matrix, as JSON or text files for front-end integration. Include a utility, visualization.py, to create and save accuracy loss plots and Grad-CAM overlays. 3. Web model conversion. Debug and fix TensorFlow.js conversion issues, e.g. duplicate weight names. Ensure the web model folder, webmodel/, contains the required model.json and .bin files for deployment. 4. Front-end integration. Adjust the index.html to load the TensorFlow.js model from webmodel/. Add interactivity to select an image for Grad-CAM analysis or input new test images. 5. Dataset experimentation. Ensure data augmentation is balanced and not overly repetitive for minority classes. Perform a trial with the current CNN and compare against ResNet18 to determine performance differences. 6. Error debugging. Address conversion errors, duplicate weight name kernel during TensorFlow.js export. Debug Grad-CAM script to handle layer not called issues by ensuring the layer is properly connected to the model. 7. Documentation and logging. Create a readme.md for developers, documenting the data flow and how to execute each part of the pipeline. Log training configurations and results in a standardized format for reproducibility.